In this experiment, we'll hang an object to a force scale, and if the object is still, we know that the upward tension will be equal to its weight. Because the net force acting on it is 0, we'll be using a force scale to measure the tension. First, we need to zero the scale. Next, we hang an object to the scale. And when the object is at rest, we record the reading from the scale. Then we put this object onto a balance and measure its mass. We have repeated the same step with different masses. Since force equals mass times acceleration, in order to get the gravitational acceleration g, we just need to divide the force by its mass.
To find acceleration, we were able to rearrange the formula of force is equal to mass times acceleration to solve for acceleration. Since the force meter gave us a force reading and the scale gave us a mass reading for those weights, we were able to simply divide the two and come up with an acceleration value. These were then averaged to give us an average acceleration as our final result, and the uncertainty was simply found by taking the standard deviation of our averaged accelerations and dividing by the number of accelerations. In this case, that would be 2.
In this experiment, we will be using conservation of energy to determine the gravitational acceleration g, and we will be triggering the swing of a pendulum using a spring. Essentially, the elastic potential energy stored by the spring is going to get converted to the kinetic energy of the object hanged by the pendulum, and this kinetic energy is going to get converted to the gravitational potential energy of the object when it's at a maximum height. So essentially, we've got the elastic potential energy of the spring equals the gravitational potential energy of the object. To determine the elastic potential energy stored by the spring, we can measure how much force is required to lengthen the spring by a certain distance, and this force will equal to the spring constant times the distance it gets stretched. Now this force is also the force it requires to compress the spring by the same amount of distance. So when we trigger the pendulum, if we compress the spring by the same distance, we know that the elastic potential energy stored in the spring will equal to half of the force times the distance that it gets compressed. In order to determine the gravitational potential energy of the object, we need to measure the mass of the object, also the height it finally reaches. In order to get height, which is this part, we can measure the angle that this object gets rotated, and we also know that this part equals the length of the pendulum times cosine of this angle. And if we subtract the whole length by this part, we'll get the height of the object, which is the length of the pendulum times 1 minus the cos of theta. Now we just need to plug this back in, and we do some arithmetics to isolate g. We'll get this expression for g. Sorry, forgot to add the 2 in here.
We used a spring, and we used the Newton scale to measure how much force it is required to compress the spring for a certain length. And from that, we found out the spring constant and therefore the potential energy stored in the spring when it is compressed. And then we set up a pendulum to which we knew the mass and length of. And then we used the energy from the compressed spring to accelerate the pendulum. And from the angle of the pendulum, we found out the vertical displacement of the mass. Since the potential energy of the spring was converted into kinetic energy and then into gravitational potential energy of the mass, using the gravitational energy equation, as we knew the height as well as the mass, we were able to find gravity from that.
Setting spring potential energy equal to gravitational potential energy, we can solve for the value of g. So to find spring potential energy, we found the force of the spring, listed here, the spring displacement when it's compressed, listed here, and to find the other values needed for gravitational potential energy, we found the mass, the length of the pendulum, and the angle, and from that we calculated the height of the pendulum swing, and using all those numbers, we were able to find a value of g listed in this column here. For our uncertainty, we simply took the standard deviation of all these g values since it was the same measurement. We used a meter stick to measure out 1 meter of a pendulum. So here from the point of suspension to the center of gravity of this mass, it is 1 meter. So we can use that in our calculation.
Hold on. Can you go back
so
to?
as you can see, the time that we got here was 19.995 seconds, which is pretty close to the 20 seconds that we should expect for the 10 swings of the pendulum. So by dividing it, we can find the time for 1 period, and then using that, we can manipulate the equation to find the value of g. Okay, so this is the 1 meter long pendulum that we created using other me.
Okay, Mystery, sorry.
Okay. This is the same pendulum that we used to find 1 meter, as its period should be 2 seconds long. So we can also use this for gravity by using the equation period time equals 2 pi square root of length of pendulum over gravity. So because we know the length of the pendulum, it's 1 meter, and we should also know the period time by timing it with an acoustic timer in 5 Fox, we should be able to find the value of gravity. So you can simply swing this pendulum and use the acoustic timer to time 10 periods. So in order to find 1 period, we're going to divide by 10. This is going to help in reducing error. When you swing it, we made sure there was, we did it at an angle less than 10 degrees and ensure there was minimal swing.
Do you have any predictions for today?
Well, it's going to be
To find the value of gravitational acceleration from a pendulum, we first needed the length of the pendulum arm and also its period. Here, the length of the arm was 1, its period we calculated by waiting for it to swing 10 times and then taking that time value and dividing by 10 just to give us a more accurate result, which gave us a gravitational acceleration value for each of the trials. This was then averaged to find our final gravitational acceleration, and its uncertainty was calculated by taking the standard deviation of all of the values for gravitational acceleration we were able to obtain, divided by the square root of the number of them. In this case, that would be root 10.
We found gravity from free-falling objects. The object we used was golf balls because golf balls are very aerodynamic. So first we picked a height and found how high it is. Then we took golf balls to the top and dropped them. Using the acoustic timer, we found the time from when we dropped the ball to when the ball bounced on the ground.
To find gravitational acceleration from the free fall of the golf ball, we were able to use the formula S is equal to 1/2 AT squared plus UT. In this case, since UT is 0, S is equal to 1/2 AT squared, and thus by rearranging, we are able to calculate for gravitational acceleration with a time and a height value. Each individual gravitational acceleration was listed here. Its average was found to give us the final gravitational acceleration, and its uncertainty was the standard deviation of all of the trials for gravitational acceleration divided by the square root of the number of trials. In this case, that would be root 27.
I'm going to go through the equation that gets the acceleration from the torque. Here's our direction. So torque is equal to force times distance. Our current situation is this. We have a distance of 20 centimeters, or 0.2 meters, And we have the force of gravity acting upon the object at this 20 centimeter mark. By substituting in the value of the distance, torque is equal to 0.2 F, and force is equal to 5 times the torque. Now we have the equation force equals mass times acceleration. By substituting in the value of force we calculated on the left, we know that mass times acceleration is equal to 5t, and therefore by rearranging to get A, we get A equals 5 torque over the mass, and A in this case is the acceleration of gravity. So this is how a torque wrench works. When you apply enough torque to it, it clicks. A distance of 20 centimeters from the axis of rotation was measured. A second solid wrench was used to hold the torque wrench in position. A bottle was hung from the 20 centimeter mark and water was poured into it until the wrench clicked, indicating that the torque had been reached. The bottle was then weighed to get its mass. Some water was then poured out, then the filling and measuring procedure was then repeated in order to get a more verifiable result. As you can see, this second measure is fairly close to the first one. The experiment began at a torque value of 2.5 Newton meters and increased by 0.5 Newton meters every trial up to a maximum of 7 Newton meters.
Using the torque wrench, we were able to find gravitational acceleration by, again, using the formula force is equal to mass times acceleration. However, in this case, force was found using the torque setting of the wrench along with the mass of our test object, and then rearranged to find gravitational acceleration. Again, we had multiple values which were averaged to give our final result, and the uncertainty was again the standard deviation of all of our gravitational acceleration values divided by the square root of the number of terms. In this case, that would be 8.
So now I'm going to show you how I corrected for the mass of the handle. The mass of the entire wrench was 351 grams, so I estimated that the mass of the handle and not the head was around 300 grams. This force was applied at a distance of 10 centimeters because it is applied at the center of gravity of the handle. So therefore, at the 20 centimeter mark where we're concerned about, the force would be 150 grams, because according to the torque equation, if I double the distance, I must accordingly have the force to cancel that out. This value of 150 grams was added onto every trial then. As you can see, the results show that the amount of force needed was fairly linear in relationship to the torque, which makes sense according to the equation for torque. This gave us a final result using that equation I detailed in the beginning of the video, that gravity equals 10.46 meters per second squared with an uncertainty of 0.13. Possible sources for error include the momentum of the water as I was pouring it in and the internal friction of the wrench.
For this experiment, we'll be using Bernoulli's principle to determine G. We've got a tube filled with water, and one end is in a container filled with water as well, and the other end is in the air, and the two ends are at different heights. And this equation is based on Bernoulli's principle. PA is the pressure at A, and PB is the pressure at B, and they're both air pressure, so we can cancel them out. Looking at the terms we're left with, they all have a common factor, rho, so we can cancel out rho. To simplify our calculation, we're going to set the height of B as 0. So the term containing HB will be 0, and this term will be gone. Now rewrite the whole equation. If the container is really large, then we can assume that the velocity of water at point A is 0, so we can cancel this term out. After isolating G, we see that if we know the velocity of water at B and the height difference between A and B, we will know G. We know that the flow rate Q at B equals the cross-sectional area of the tube times the velocity of water at B. The flow rate also equals the volume flowed through B over time. So after doing some arithmetics, we obtain the expression for velocity of water at B, which is changing volume over changing time times the cross-sectional area of the tube. We set up our experiment just like how it's like in the previous diagram. We measured the height difference, and we filled the tube with water. We'll be using acoustic stopwatch to measure the time. This person will yell to start the timer, and at the same time she will open the tube. And at 10 seconds, she will close the tube. We measured the volume flowed over this 10 seconds using this baking cup. And finally, we measured the diameter of the tube using a caliper in order to calculate its cross-sectional area. We'll do a total of 10 trials, and after each trial, we'll dump the water back in to make sure that the water level is consistent.
To find gravitational acceleration, we were able to use Bernoulli's equation, since we know the values of the velocity of the water from the water flow, and we were also able to calculate the size of the cross-sectional area of the pipes. We were able to find the velocity, we were find the total volume flowed in 10 seconds, and from that we were able to find what gravitational acceleration from each of our trials. We then averaged to find a final gravitational acceleration value, and data was calculated with the standard deviation of each gravitational acceleration result divided by the number of results.